Okay, so suppose I can get started now. Basically why I'm here today is because I did a master project, or graduation project related to LLVM. And the whole idea is that if someone by any chance do the very same thing, then you already got a head start and you have my mistakes and my work. So the topic of my graduation thesis was to connect LLVM with a worst case execution time tool. And I will explain what this means in a minute. So the talk will be following things. So first one is what is this worst case execution time and worst case execution time analysis, because it's not really related to LLVM at all, but it is related to my project. Yeah, and why would you connect LLVM to a worst case execution time tool instead of putting it into LLVM itself? And what tool to pick, which I already did, is a suite tool, and I have my reasons for it. And there are ways of what data to use from LLVM data structures, and I will talk about it. And I did some things with a specific architecture, the ARM Cortex, which I will share, and my experiences with this approach, this whole concept in general, what I'm doing, and I will then conclude. So first of all, worst case execution time, which is a bit of a silly concept, but imagine that I ask you to design a software routine for pressing the brake on a car. I suppose you will need to, by design, have some guarantee that it will eventually finish, because then your brakes won't be activated and your car might crash against a tree or something. So the worst case execution time is the very longest time a piece of code can take. And you might have, by your design, have a requirement on this. So how would you determine this worst case execution time? Well, you might say you just run your program with all possible inputs. Well, that turns out not to be easy or not possible, because in non-trivial code there are way too many paths to cover. So for example, if you would have a function with two 32-bit integers, and you would have to run the program lots and lots of times to test all possible values. So you might say in practice you might have to do less, but you're never really sure if your program is arbitrarily complex. So there's a thing called static analysis, which instead of running your code, it will look at the semantics of the code and then try to do some mathematical derivation, and in order to get a worst case execution time bound. And the theory of this is called abstract interpretation. So I would like to discuss this again by a form of a graph. So say you have on the y-axis here the probability of a path occurring with certain inputs. So that would mean, and on the x-axis the execution time. So it might be that on the left here, the red arrows, that you do a lot of measurements and hit most paths, but you're not sure, you cannot test every path, every possible input. So you might miss one, it might be longer, so you might have a big problem if that happens. So the theory can then do a bound, worst case execution time bound, with static analysis to find a bound that's usually a bit higher than the real one that you cannot find out, but it's still, at least it is safe. That's what the theory does. So so why connect LLVM with a tool that can do worst case execution time analysis, and why not just build it into LLVM? First of all, that's really hard because theory is not really easy. You basically need to have a PhD in computer science or a really specific mathematical field to be able to understand this. Secondly, there are parts in the whole idea of this is that you can do worst case execution time analysis alongside the code that you're compiling, because you have the code available in data structures in LLVM. So you can reuse information about the architecture that is put into LLVM by means of scheduling and so other things. So that's basically a table gen. So yeah, there exist open source tools that can do worst case execution time analysis. So why not connect them to LLVM? That was the whole idea. So the tool suite was my decision for my project, and it's a tool made. It stands for Swedish Execution Time Tool. So yeah, from Sweden. It's open source, but a bit silly open source, meaning that you have to email them to get the code. So that's weird. It has an interface language ALF instead of running on a binary. So usually the tools reinterpret the binary, and then they do control flow graph reconstruction. So you have if else and so on. And then they do take the semantics from the binary and do static analysis. But this tool is a bit different because you have this ALF language. So you can basically, you're not tied to them only supporting the various binary formats. There are different tools, well, except for Suite. Most of them seem to be research, Suite is also a research tool. Most of them seem to be abandonware or research tools. And there's one proprietary tool called AIT by the Absinthe company, which is, as far as I know, is completely dominating the market. So yeah, there's not even an open source alternative that is widely used in this stuff. The Suite tool, it's a bit, has a bit of a specific way to use it. Basically, they ask you to change your code semantically to this ALF language, and it does analysis on this ALF language. So it can then find out which basic blocks will be executed and not ahead of before you run the code, which I find to be really interesting. So it is the Suite tool. Needs two inputs. It needs ALF code of your code, which is semantically the same, so the same calculations and so on. And you can also model your registers for memory in this ALF code. Next to that, it needs for each basic block, it needs the amount of instructions that it will take on your machine. Because Suite doesn't know it, it's just, well, it does analysis on ALF. So you're expected to do like take into account caching and pipelining and other things, and just provide them a list of basic block names with cycle counts. But all of this stems from the control flow graph as necessary to have. But we have this in LLVM because it's in the data structure. So this is a small example of ALF code which you probably cannot read, but I suppose you can look up the slides later. But this would be an addition of two registers. And the first thing you notice that it's really verbose and annoying to read. And there are lots of 32 here, meaning that's the bit size. So they are really specific on the bit sizes that you use, because that's where you get the possible ranges of values from your calculation. Other thing here, what you probably cannot see, is that the add does two loads from frames called R0 and R1, which is these frames you can design yourself, or basically a name with bit size. And Suite has arbitrarily an amount of operators from which they claim you can model your instructions of your instruction set, so add and so on. So, so next was my approach in the project to connect the Suite tool with LLVM. So the whole thing is the output ALF from LLVM, because Suite uses ALF, so that's, you might say, is easy. The thing is that this ALF code needs to be exactly semantically the same as the instructions on your processor. So if you make a mistake, then your analysis is wrong, and the worst case execution time is wrong, and that's a really big problem. So the ALF code can be obtained from TableGen. From TableGen they use called in the DAC so the instruction selection, when you go from IR code to the backend, you have they use DAG patterns, and this is essentially is the semantically the meaning of what instruction does. So this is what I use to output ALF code from the instructions from LLVM. So from the right now we should probably discuss this picture below. So so this will be an easy overview of simplified overview of LLVM. So to the left you would have Clang or the front end, and it will go to the intermediate representation, and then there are done architecture independent optimizations, and then you would go to the backend or a backend, the LLC tool, and there you have two key data structures: the machine instructions and the machine code. And the difference here is that when you decompile assembly code or a binary, you go to machine code, and then you do not have the control flow graph, so the decisions in the code, because that's really difficult to retrace when you have decisions made on values in registers that you do not know ahead of time. Okay, so in machine instructions, that's where you do have the control flow graph, and the idea here was to go from the machine instructions to ALF code at the very last moment, when all the optimizations are done, when you pretty much can say it will be the same as that you output to the binary. And this would have been at the pre and mid pass function to your target something a path config class in your backend. So yeah, the ALF code per instruction, the idea is that this semantic information of your architecture is already present in LLVM, and that we're reusing it to output ALF. So the idea was to construct a TableGen backend, as they call it, which is basically when you interpret TableGen, you get a set of records, and with these records you can do anything you want. So so you could have every instruction and information about each instruction. So what I did in the project is to generate a function that, based on the machine instruction object, outputs ALF code, and this ALF code is then determined based on the DAG pattern field of each instruction. The thing is that not every instruction has a DAG pattern, so you can customize this by doing a complex node or something, and so there's also the option to do there's required work to write C++ code for generation of ALF functions, ALF code, when this is not available. That's a bit annoying. Further on, the compiler does not even care about conditional flags. So in a processor you would have an instruction, then various flags are set. For example, is the result is negative 0 or carry or something, and then based on these flags, usually processors do this, but they decide the decision is made on these flags. But an LLVM, for example, in the ARM instruction that does an add, an LLVM is not really registered what specific flags are set for each instruction. So this was a bit annoying, and I had to basically assume that these 4 flags existed, which is not target independent at all. But, so I tried to do this for the ARM Cortex, try to get the worst case execution time analysis going, and then to generate all this ALF code from TableGen to see how far I would go. This turned out to be a lot of work, because there's lots of instructions, and lots of them don't have DAG patterns defined, so I have to write C++ code by hand to output ALF, which was annoying. So I mentioned earlier that the suite tool also needs the cycle count worst case for each basic block. I made the processor I selected has some branch prediction, so that I was forced to take the worst case execution time listed in a datasheet, but it works and it's probably safe. So the thing is that you can get analysis from the suite tool, and but you're not sure if this analysis with the ALF you obtained from LLVM is correct, semantically the same. So I had to make tests against a simulator where I checked basically the register values. This was it did work, but it's really annoying because you're compiling a whole C code, then you get some arbitrary code that is selected and scheduled, and at the end you would have to test this ALF code with the suite tool with the binary and then execute it in the simulator. So it's not really easy to find select one specific instruction and then generate ALF for this. So I had some major issues here. Furthermore, there are two things that I discovered for that's a good reason not to do this project again. So another reason why I'm here. I made the assumption at the very beginning that all the code you compile is available in LLVM, and for each instruction you know the semantic meaning, and you can obtain this from LLVM. Well, this is not true, because for what happens if you have a processor that does not, for example, have floating point instruction? LLVM doesn't have these instructions defined in the code, or what would happen otherwise, but it will instead link to a function of the libgcc or the compiler IT library, which starts with __ something. For example, multiply division here, I believe. So this code is not available in LLVM, and I cannot make ALF code for it. That's really annoying, a big showstopper really. Furthermore, when you define globals in LLVM, the position of these globals is only later determined in the linker, so that the compiler also doesn't know it. So that's another big problem. So, yeah, so basically I'd like to conclude with a small summary and what I tried to do. So I tried to add worst case execution time analysis to suite, to LLVM with the suite tool. For this I just needed to output ALF code, which was semantically the same to the instructions of that you're compiling from LLVM. I used TableGen for this to make generate code, and that you can then use in your backend. I managed to get it working for the Cortex M3 for some programs that do not have these, for example, floating point calculations. I found out that I required to know the conditional flags of so -0 and so on. And these are not in TableGen because the compiler doesn't care about it, apparently. Yeah, and so bottom line, LLVM does not have all the information required to do this, because for all general code or non-trivial code you can find, because parts of the functions are in libgcc. That's really annoying. So this could probably improve with well, yeah. The backend only the TableGen backend I made only looks at fixed patterns, so set, add, and so on, and so not nested add, DAG patterns, that is. I don't consider delay slots of instructions, so if you have an instruction and a few cycles later the registers get updated, that the ARM did not have. In my project I could not finish the M3 instruction set, and it would have been needed to specifically select a libgcc version and then handwrite all the ALF code for these, so for the functions that your processor doesn't have, so floating point and so on. You would have to supply additional ALF code that needs to be the same. Yeah. So some links, if you want to give a go at this project or continue it. So first is the code I have. I put it on GitHub. I made a syntax highlighting file for Vim because there was not one available, and don't think there were that many users on the Suite mailing list. There are only 25 users. I don't think the tool is that much known anyway. So, the Suite homepage is, if you just Google Suite, you don't get to this tool because, well, other meanings. And there's this specification document of the ALF language, the Suite. So yeah, okay, that's it. Thanks for listening.
We have about 10 minutes for questions.
Oh yeah, okay.
Anybody got any questions?
Yeah.
So if I understood this correctly, what you did is because you don't have the conditional flags available,
Yeah.
you assumed a specific set and always used that.
Yes.
But doesn't that mean you completely eliminated certain code paths entirely from the code and which makes your WCET analysis entirely wrong?
So basically,
No,
repeat the question.
Oh, okay. So what he asked is that I assumed there only to be 4 conditional flags, so negative, 0, carry, and overflow. And you mentioned that this would make the analysis wrong.
Yes.
Yeah. Well, it would not make it necessarily wrong, but it would make it only possible for processors that have only these 4 condition flags. So the specific processor I use, but I suppose it could be adjusted to make some kind of function in TableGen that would then make it possible to define more status flags in TableGen. But I did not look into this much. So, did I answer your question? Sort of?
Okay, so I think there's some misunderstanding here, right? So when you say you assume the flag, did you assume a specific value for the flag, or did you consider both possible values?
Oh, I meant I assume the existence of these flags. And for example, these are all the patterns I considered. For each instructions in TableGen has like these patterns defined. And so for set register with add or something. And from this instruction I set and specific flags, and I don't consider any other flags. So if you have a really weird processor that based on the bit size, say you have a 30-bit operation, and then it considers differently the first 16-bit and the higher 16-bit, and sets different flags for it. It's not modeled because it's really specific to only these 4 flags. It's a bit hard to explain. So, any other questions?
Did you consider compiling compiler RT to bit code? So you potentially basically use that to get a fast sort of way of getting the floating point routines?
Oh no, not at all. You mentioned the compiler RT and then compiling it to bitcode. So, but is this IR bitcode?
Yes, something like that. So then you could then link that with your program, and then you would then have all of the compiler RT routines that you needed for the floating point available to you to then translate to ALF.
I need the semantic information of each function that is defined in compiler RT. I need to transform this to ALF. That's what I would need to get it working. But I might have a look at it.
You have some general C codes, and the compiler will output intermediate representation that you then translate to ALF.
Yeah, sort of.
Why can't you compile compiler RT and
Oh.
it in and then translate it to ALF?
Oh yeah, that's. I did not think of that.
Right.
Good one.
Yeah.
So.
Either compile it and use it at the IR level, or compile it to ALF and kind of link it in Suite or whatever.
Yeah. Oh, no. Okay. Any more questions? Or? Yeah.
With the other issue you mentioned, the linking issues, if you did an LTO build, would that fix the linking issues you had, or the actual symbols that the linker is actually adding that
Uh,
that LCO wouldn't solve.
mm,
So is it just the actual addresses you need, or is it
Uh,
missing?
Now you need to have, for all the code that would go through the compiler, you need to have equivalent ALF code. And the thing was that some functions that, or some instructions that you cannot do on your processor, the LLVM just inserts a call to a function that is linked later by, after the compiler is done. And you don't have this code available in the processor, or in the LLVM. So, for example, a function that would do then the floating point addition, but then in software with different instructions. And this was not available in LLVM at all. That was the issue. Mm.
Yeah,
but,
isn't that solved by
yeah, yeah.
suggesting that?
Yeah.
Because you mentioned two issues. One was the compiler OT functions, but you also mentioned something about other linking it. Because you listed two issues.
Oh wait, yeah.
Number two.
I think I misunderstand you. Yeah. So the second one is that the compiler of some
So these globals, what I was asking is, if
yeah.
you did an LTO build, so link time optimization build, would you get the globals that you would need, or does that not solve the problem?
Well, I'm not familiar with link time optimization.
So
So
there's a link time optimization basically is you delay the machine code generation until you
know the location of all.
you basically you create LLVM IR but don't generate machine code. You have all these object files but they actually have LLVM IR in. You then ask LLVM to link all this together so you get one huge LLVM module. Then you generate machine code.
Oh, yeah, that would perfectly solve the problem. So thanks a lot. So then I would in LLVM would know the location of all variables instead of in the linker.
But it doesn't, that the code generation happens before the linker lays out any of the addresses, so you wouldn't know the final address.
Yeah.
But you would know all the globals that would exist, but you wouldn't necessarily know where they were at the link time optimization.
Yeah, that's the problem. Yeah.
Basically, the compile timing is measured doubles.
Measuring doubles.
The compile time may double.
Oh,
when you
oh.
do time optimization.
Okay, but in this case I would not care. I suppose. Okay. So
Any more questions, or should we?
yeah.
What is your opinion about doing WCET on, I would say, higher CPU, so CPU with cache or formalization?
My opinion about using this with cache, processors with cache, or caches are a big problem with worst case execution time. Usually when I encounter these tools, they either have a really complex, for example AI2 has, I believe, some cache analysis, but cache is a really big problem. You don't know basically what's going to happen, so they always expect a miss. But the SWE tool does not do any cache, so yeah. I would have to do it myself and I did not. So.
We're going to have to stop there to change over.
Yeah,
Thank
okay.
you for the presenter again.
Yeah.